Hi, my name is Karla Davila, and this is my project for Statics 1. I did my project on the streetlight that's outside my house. I took two pictures because the camera would either focus on the streetlight or the ID. So I just put two for good measure. So this is my free body diagram that I created. And for my assumptions, all the dimensions and weights are based on my references. I made most of everything the maximum they could be to see if it would increase the probability of it not withstanding the high wind load, which is why I also added an angle for the 30 pounds. I could have just made it go straight down, but I wanted to give the maximum moment on the Z and Y axis. So my goal is just for it to fall. And for the wind load, I calculated that later on the online calculator, and I concluded it to be 8,670 pounds. For simplicity's sake, I'm just putting it at the center of the pole, which should be 14 feet on the z-axis, and parallel to the x-axis. And for the base of the pole, it's a fixed support. Like even the one that's outside my house isn't bolted down. I believe it might be bolted down underground, but we're excluding all the underground stuff that's going on and focusing just on the above ground. So for my knowns and unknowns, my knowns are the weight of the pole, which is 660 pounds, the weight of the light, which is 30 pounds, the angle between the metal rod and the pole, which is 30 degrees, the wind load, which is 8,670 pounds, and all the positions. My unknowns are the angle of the 30-pound force and the force of A on the X, Y, and Z axis, and the moment force on the X, Y, and Z axis. So my equations of equilibrium that I'll be using will be the sum of the forces on the X, Y, and Z equals 0, and the sum of the moment force on the X, Y, and Z equals 0. So first we find the missing angle. So the position of the force is at 0, I didn't put it in because it was 0, because it's on 0 on the x-axis, and it's negative 9.17 on the negative y-axis because it's on the negative side, and 6 plus 3.17 equals 9.17. And then adding the 30 feet, so 30K on the z-axis. And doing my calculations, I found that arctan of 9.17 over 30 equals 17 degrees. So 17 degrees will give the maximum moment. Next, we find the force of A on the x-axis using the formula, the sum of the forces on the x equals 0. So after doing the calculation, we find that the force of A on the x-axis is equivalent to the wind load, which is 8,670 pounds. Similarly, we also find the force of A on the y-axis using the formula, the sum of the forces on the y equals 0. So we also find that the force on the of A on the y-axis equals the force of the 30 pounds on the y-axis, which is 28.7 pounds. And again, to find the force of A on the z-axis, we use the sum of the forces of the z equals 0. So it's the force of A of Z minus 660 pounds because it's on the negative Z and it's the weight of the pole, minus the 30 pounds times sine of 17 because it's on the opposite of the z-axis, right? So we use sine. And with these calculations, we find that the force of A on the z-axis is 669 pounds. Now to find the moment around the x, y, and z axis. So the sum of the moment on x equals 0, so it equals m of x minus the force 30 pounds on the z-axis times y, which is 9.17, minus the 30 pounds on the y-axis, the force that is on the y-axis, times z, which is 30 feet. So we find that the moment of x equals 780 pounds. And for the sum of the moment of y, it equals 0, right? So the moment of y minus the wind load, because it's the force on the x-axis, times z, which is 14, because remember that it's at the center of the pole, so it's 28 divided by 14. So the moment of y equals 121,380 pounds. And the sum of the moment of z, I just found to equal 0. So in conclusion, I do believe the light post will remain static during the highest winds in El Paso, which is 69 miles per hour, because the PSI for sidewalk slabs is usually around 35,000 to 40,000. Therefore, it can withstand the moment about y and the moment about x. And that concludes my presentation. Thank you for watching.